Let's first understand why we need continual learning. So here we have something like the Netflix recommender system. The aim of this system is to use information about the kinds of media you have watched to give the user a suggestion of a movie or TV show that they can expect to like. So in this example, the user is given the suggestion of Interstellar, because the user has previously watched Tenet, Inception, and Black Mirror. However, the user may watch more movies as time passes, such as, let's say, this user decides to watch Incredibles 2. Now, the recommender system must be able to adapt to incorporate the new information, as well as accounting for the old information. But we don't want to retrain the whole system using all the old and new data together, because that is very inefficient. We only want to incrementally change our system to incorporate the new data that the system has received, but not forget about what was learned from the old data. So in words, continual learning is a task in which data continuously arrives, and systems must adapt to perform well on all of the data that avoids revisiting all previous data at each stage. Let's first discuss the underlying principles governing Bayesian machine learning. We will be using the following notation for the training, test, and weight parameters. In general, any discriminative model is required to make a prediction of the test output conditioned on the test input and all the training data. From a mathematical perspective, this can be achieved by integrating the product of the test likelihood and the posterior distribution with respect to theta, where theta has been learnt at training time. Putting it more intuitively, the prediction is an expectation with respect to theta of the test likelihood, where the distribution of theta is assumed to be the posterior distribution from the machine learning model. Okay. For the continual learning setup, we have NT data points at each time step t. So we can see that the new data introduced at each time step t. We will denote dt as the outputs at time step t, and in general we will suppress thinking about the inputs as it just clutters the maths. So all the datasets from time step 1 to big T will be denoted in the following manner. And hence, this is the posterior distribution we are interested in to be able to make predictions. So we need a way of finding this posterior distribution. Okay, because the datasets are independent, I'm going to break up the final dataset term from all the old datasets. From the definition of given probability, we know the result is proportional to this line. And hence, from the definition of intersection, we can write it like this. Note, we could have jumped to this line directly by using Bayes' rule. We can eliminate the dependence on all the previous datasets for the second term, because all datasets are independent. Now what we have here is a very useful result, because we have defined a recursion where the current posterior is simply proportional to the old posterior multiplied by the current likelihood. Simplifying the notation even more, we have the following update equation. So this is good news, because now we have a way of finding the posterior distribution at each time step for continual learning. However, there is still one issue. We cannot usually find closed form expressions for pt of theta, because the distributions on the right can be very complex, and thus multiplying them becomes intractable. Therefore, we make an approximation where we select a certain class of functions called q, for which multiplying is now tractable, and hence we can find a closed form solution for the left-hand side. Then we choose a specific q, which is the best approximation for p out of all possible q's in the class using some metric. A typical class of functions chosen for Q is the set of multivariate Gaussian distributions, which are defined by a mean and a variance. Now we can write our update equation in terms of Q's. It looks complicated, so let's break it down. We are trying to search over the whole space of big Q and choose the distribution which is the closest to the distribution Qt minus 1 multiplied by the likelihood. Closeness is measured using the KL divergence, which is used to find the distance between probability distributions. Note, the ZT is simply a normalizing constant, which we don't really need to worry about, as it only ensures the expression is a probability distribution, by which we mean that the sum of all probabilities is equal to 1. And that's it! We now have an approximate update equation for the posterior distribution at each time step where we needed to make the approximation in order to be able to find closed-form solutions. And hence, we can easily do the prediction at each time step using the Gaussian posterior distribution of that time step.